Oh yeah, that's what I meant to tell you guys. Thank you. So yes, it is true. You can retake. Actually, it's not an option. It is required for you to retake it until you get a 90. If you already got a 90 and higher, you can retake it to get 100. But everybody by the end of this is going to have at least a 90 on their nomenclature quiz when I put on Power School. So you absolutely have to do that. So what I would encourage you to do is, if I can get it back to you today, I will. If not, study tonight. Try to retake it tomorrow during TLB. If not, tomorrow after school. If not, Monday during class, Monday during TL, Monday after school. We'll make it happen. Monday is review day. I pushed y'all's test to Tuesday. Okay? Monday is review day. Question?
Is no one's practical right now?
No, I don't put them in until I finish them. First of all, step 1, finish grading. Step 2, if they're above a 90, I'll put them in. Okay, so you've probably seen this has been sitting here. You're supposed to be writing down some of it. We talked about VSEPR already. VSEPR is that valence shell electron pair repulsion. It's just basically saying electrons are negative, they push other electrons away, and when that happens, it creates a shape. We've already been exposed to some of the shapes, and we're actually going to see them in 3D today. The 3D part is so valuable because you've been drawing them 2D, 2D, 2D. You need to be able to see them on 3D, and that's going to be something that you will build. Before we do that, though, I need to expose you to something called Expanded Octet. But for that, though, there are some shapes we've already been exposed to. So do you guys remember the shape of the 4-legged one? Tetrahedral, right? And this is kind of what it looks like. It's like 4 big balloons attached to each other. And if you think about 4 balloons, they can't really sit at a right angle with each other. They sit a little bit obtuse. So we're going to start to see some of these in terms of their bond angles as well. So we've drawn methane like this. Probably, if we had to draw it, we counted up. We said, okay, 6. There's methane. 6 electrons from carbon plus 4 hydrogens, each carrying 1 electron. So, I'm sorry, not 6 from carbon, 4 from carbon. Ooh, 4th group. So that's 8 electrons, 8 valence electrons in our structure. So you always want to make sure you're counting your valence electrons before. But when you draw it, and you count for all the ligands, there are already 4 electrons drawn there, so that's why that works. 2, 4, 6, 8. That structure looks 2D, right? And it looks as if it has a right angle there, but it doesn't. It actually looks kind of like this, so it's got an angle like a little bit more obtuse. That angle is 109.5 degrees. If you just know it's above 100, I'm good with that. So we're going to start to kind of incorporate what the angles are and how they're oriented in space. So that's why that drawing is here. Notice a little lower, I have an example, NH3. What is the name of this? We talked about that. Ammonia, right? Sounds like ammonium. Ammonium cation is NH4 1+. That's a polyatomic. This is ammonia. Okay. This one has a lone pair. Let's have this on your dot structures. That one right there. It's NH3. So you count it up. 5 electrons from nitrogen plus 3 times 1 electrons from hydrogen. So that was 8 electrons, 8 valence electrons. That structure has 3 ligands, which is 2, 4, 6, so only 6 electrons. There had to have been an extra electron, lone pair on nitrogen. And this is what it's doing. Remember the repulsion part of VSEPR, valence shell electron pair repulsion, okay, theory? The electron cloud is really, really negative, so it's pushing down those to make it look kind of like a pyramid. So it's like this. It's got like 3 legs and a lone pair up top. It's like a spider. I don't know. But that's what it looks like. So that structure, that geometry is called trigonal pyramidal, which is because of the whole triangle, 3 legs, and it's shaped as a pyramid, simply because it's being pushed away. So I just want you to start visualizing this. If you can in your head, it's kind of hard, but we're going to work with structures today. These structures we need to talk about because there's someone like that on your Prop Set 7, 8. And if those of you who've already started, you've seen some similar ones. First off, let's do ozone. What is ozone's formula? O3, good. So write this example down. I'm going to do this one and maybe that one. I'll do 2 here. Maybe 1 more. So ozone, tell me my quick steps here. What do I do? First step, count valence electrons. 3 times oxygen, which has how many? 6, it's in group 6, okay, so that's 18 electrons. All right, so who's in the middle? Oxygen, right? We can't really get that one wrong. And then guess what's on each side, guys? Oxygen. You guys are so smart. Okay, so we have oxygen everywhere, bonded together. Now, what do I need to do? 3 times. 3 times oxygen. 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 3 times oxy get octets on everybody, right? So give everybody electrons. You can have electrons, and you can have electrons, and you can have electrons. Everybody gets electrons. There you go. Okay, so yeah. So here we have all octet everywhere, right? Double check our count of electrons we just put on our structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We only can have 18, so what's our goal here? What do we need to do? Erase 2 lone pairs, maybe here and here, central and on the side. And instead of giving them 2 lone pairs, you just make them share. That's how you fix that problem. Just say, hey, you don't get individuals, you have to share. So then that's 18. I chose to put the double bond on this side. We could have done the same thing and put the double bond on that side, but not 2 double bonds. Because if I put 2 double bonds, well, how many electrons would I have? 16. And that would be too low. So this structure here is equally acceptable as this structure here. That's what I'm saying. So if these 2 things are equally acceptable, you can draw a double head arrow between them and say it can be either one of these. We call those resonance structures. Did you define that on Reading Guide 8? Remember that? Resonance? So resonance structures just means they have 2 valid Lewis structures. Essentially, it's like a flipped version of it. That's all. Okay, so also we can draw things that are in ion form. The ion form of a polyatomic really shows you its structure. So what's that polyatomic's name? It has a name. It's a polyatomic. It's one word. This one. Sulfate. So sulfate because it's sulfur and 4 oxygen. So that's sulfate. Has a 2 negative charge. That 2 negative charge means overall there are 2 additional electrons on that structure. So total electrons are here. Are coming from sulfur. What group? Group 6. So it's in group 6. So it has 6 valences plus 4 oxygens, each carrying 6 each as well, because they're also in group 6. Then you have to add 2 electrons because there's 2 extra negatives. So you just add 2 more electrons here. So if it were a cation, what would you do? Minus 2 electrons, or whatever number it says. So this gives us how many electrons? 32. Okay, next up. Put the S in the middle, because that's our singleton. So the singleton goes in the middle, surrounded by oxygens symmetrically. So we had 4 oxygens. How many electrons have I used thus far? 8. So I need to add, what do I need to do to everybody else? Octet them up, right? So I like to just throw electrons up here. Okay? So now that everybody has octet, double check your count. How many are here? 8, 16, 24, 32. So that's good. And this is actually mostly correct. I'm not going to tell you everything about Lewis dot structures because you don't need to know everything. You just need to know that this has 32. Everybody's got octet. We're good. But to indicate that it's an ion, we do have to put a bracket like we did in our ionic structures. Put a bracket and then put the charge on the outside. That's it. That's just the one extra step you have to do for polyatomic ions if I ever actually had to draw them. But I wanted to do this because some of you are like, what are the polyatomic ions? Like, why do these group together? Why do we have to keep these together? Why do we have to put a 4 there? Because literally, this is what the polyatomic ion is. It is a poly, so many, atom ion. Polyatomic ion. It's just a big old ion. But it's got a lot of stuff connected to itself. So that's why we just have to be aware what their names are, but that's actually what it looks like. So how would ammonium look? Tell me my process, quickly. Fine, tell me my process. Always start with what? Just because I know you guys will forget to count your valences. So count your valences. So nitrogen's in group 5 plus 1 each. Okay? Minus 1 because that plus 1 charge indicates overall it's lacking in electrons, so you subtract 1. So how many electrons is that? 8 valence electrons. Okay? And then draw it. Nitrogen with 4 hydrogens. Okay, next. Why am I okay? Why is this correct so far?
Because you've already used all 8.
I've used all 8. Does everybody have octet? Okay. No, this is the exception to the octet rule, right? So nitrogen has octet. It needs octet. Hydrogen is small. What does it have to have? Maxes out at 2. So I like to call that the duet rule versus the octet rule. Everybody gets octet unless your hydrogen, there's actually a couple. Hydrogen helium, and boron. Boron is good with 6 electrons. Helium's good with 2, and hydrogen's good with 2. This is just something I wanted to tell you before you got to your lab, because what was one of the ones on your lab that had boron in it? BCl3. So that's actually my next slide, and I'll show you an example of that. Okay, so I want to review, bracket 1+ charge like Zach said, because it is an ion, so we have to indicate it that way. So let's walk through some more exceptions. Let's go through expanded octet. What do you think that means? More than 8, okay. More than 8, expanded octet, more than 8, and then that one exception with boron. So 80% of everything will have octet. There are a couple of exceptions. So I'm going to change this to boron trichloride, like your lab says. Okay, so let's go through this. And if you had some questions, I'm answering questions as we go, so I'm trying to make sure I take care of those before we get to the lab. So boron trichloride, first thing you did was what? Count. So boron carries how many electrons? Valences. It's in group 3, so it carries 3 plus 3 times chlorine. 7. Chlorine's in group 7. So everybody okay on figuring out? You look at group number is valence number. That is how you count. So then how many electrons total? 24 electrons. Okay. So this is our starting, and then we say, okay, central atom, boron, and then you just kind of make a symmetrical kind of attachment system here. So chlorine, chlorine, chlorine. That's 1 bond, 2 bond, 3 bond. Okay. Now what do I do? Everybody has octet, right? So I'm just going to add dots until octet on the chlorines first. And you're like, okay, boron doesn't have octet. Some of us probably went ahead and tried to actually erase a lone pair and make it share instead, which is okay. I get it. That's fine with me. But I just want to make you aware that it can accommodate 6, and it's okay with it because boron's really tiny as well. So it's on that side of carbon. It's pretty small in terms of like number of electrons it can handle. So if you put this, or you put like boron double bonded to chlorine with only 2 pairs of electrons out here, that's fine. But that's more unlikely because is chlorine electronegative? Who's more electronegative, chlorine or boron? Chlorine or boron? Boron. Chlorine is like way over here at group 7, right? So it's 1 away from noble gas. It's actually super electronegative. So it's very unlikely that chlorine's going to be nice enough to share another pair. It's more likely that chlorine's going to be mean and want to have all 3 paired to itself versus have to share another one. It's just more about their trend and their electronegativity. So that's one exception. Second type of exception is called expanded octet. Okay? So things that are from sulfur and over. I'm going to point up here on the PR table. Phosphorus and over. So phosphorus, sulfur, chlorine, argon, that little group right there, and down. So phosphorus, sulfur, chlorine, argon, and down. That's all going to be having access to D block. And D block is just 5 extra orbitals. So they have extra places or pockets to put extra electrons. So they can expand octet. And that's just one other exception. So was this an example on your sheet? Yes? So tell me your step-by-step process here. I'm going to show you how to draw this one. Count, so tell me what I got here. From phosphorus. Phosphorus is in group 5, so you have 5 valence electrons. Plus 5 times 7, because chlorine's in group 7, so total 40 valence electrons. Okay, so this one actually makes sense because all you have to do is take your phosphorus, which is in the middle, is our singleton, draw 5 bonds coming from it. Looks like a little man. Okay, arms and legs. There we go. Okay, and then what?
Each chlorine has the octet.
Octet. So octet to everybody. Sometimes it takes a minute to draw, but do put your dots because if not, the Lewis structure is 100% incorrect. Okay. Does phosphorus have at least octet? Yes, it actually has 10, and that's okay. Okay, so phosphorus is okay to have 10 electrons because it can expand octet. Chlorine technically could, but chlorine, like I said, is more electronegative. It doesn't want to share any more than it has to. It just shares enough just to get attached. That's it. So this shape is weird, though. This shape, tell me, is it on the back of the card? 5. Yes. Okay, what is it? Trigonal bipyramidal. So trigonal bipyramidal. Okay, so I'm going to try to draw this on a 2D board here for you. And it's not going to be pretty, but we're going to try. So what does this look like? Looks like this. Let's see here. Triangle in the middle. This is kind of like the equatorial triangle. There's a chlorine here, chlorine here, chlorine here. So phosphorus in the middle. And then there's a chlorine up high. There's a chlorine down low. And it kind of just takes on like... What? Are you talking crap about my drawing? Because I didn't grade your papers. That looks kind of like a pyramid. It's like this is an equator, and this triangle are pyramid on top, pyramid on bottom. Oh. That's kind of what it looks like. Yeah. I know Huh? That's just me drawing, Madison. Gosh. I will let you see that when you draw it. It looks much prettier. I mean, when you build it. Okay. So before we move on from here, though, I want you to actually draw your dipole moments on the structure, and let's talk about the molecular polarity, because we've talked about bond polarity. That was the second column, yeah, or first column. We talked about molecular polarity, and then I'm going to set you free to laugh, because this is something that's so valuable to see in a 3D picture, because it's really hard to figure it out 2D picture-wise. So, what's the polarity difference between P and Cl? What's the numbers?
2.1 and 3.0.
2.1 and 3.0. Polar covalent, non-polar covalent, or ionic? Polar covalent. So this is literally what should be in that second column. Okay, you're drawing the P bonded to Cl. You write the numbers. You say, oh, it's polar covalent because it's above, it's 0.9. Now, who do I draw the arrow towards? Cl. So it's pointing the arrow towards Cl. Okay. So at that point, this can be superimposed on the structure. So I'm going to draw a arrow pointing towards chlorine, just right next to the bond or on top of the bond, whatever floats your boat. Okay. So what is that really telling me about the electrons, where they're living? Are they living closer to the middle of the atom or closer to the outside? Outside, because it's basically showing you electrons are kind of scooching here, 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 and here. Did you see me draw any positives anywhere? No. So I have negatives, kind of just partially negative all the way around. So if you think of it like a globe, think of it as a big sphere. And if all of this sphere has equal amounts of electrons, do you have opposite ends? If everything has equal amounts of electrons, do I have opposite ends? No, it's negative, 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 right? Okay, so if I don't have opposite ends, can I be polar? What's the definition of polar again? Polar means like north and south pole, opposites. So if polar means opposites, based off that definition, is that molecule polar or non-polar?
Non-polar.
Non-polar. That's it. So basically, we just figured out what molecular polarity was based off, 1, the dipole moment, and 2, how it looked geometrically, how it looked in space, based on its shape. So you can imagine that some shapes don't allow for everything to have equalness across the board. Some shapes are going to force it to be polar. Yeah.
So would like a tetrahedral force it to be polar? Because...
No, the tetrahedral actually is kind of like a sphere in itself, because it's like one's up here, here, and here. So it's not exactly like a sphere, but it does have equal distribution across the board. Yeah.
So the negativity is polar covalent.
Yes.
Then the molecular polarity is non-polar.
Correct. So this electronegativity for this, or the bond polarity, is polar covalent. So when you say the word covalent, to me, I know you're talking about a bond is covalent. But if you just say non-polar, I'm assuming you're talking about the molecule, the whole shebang. All right, and I have all that written out for you. This is a long part of today. Not long, a little longer than I want it to be. Write down what you need to based off what we just said. This part here, 1 and 2, those are the 2 things we just talked about. But this is going to be your go-to on how you figure out if a molecule is polar or non-polar. And keep your dots on your desk so I can see them as you guys are writing this down. Dots on your desk. scroll down for you now? Just a little, well, actually there's not much to scroll down. Let me start. So like we just said, anytime we're talking about molecular polarity, you think of the whole shebang. You think of after you've drawn the bonding, or the geometric shape, and after you've looked at the bond polarity, that's the only time you're going to be able to actually figure out if the molecule is polar or not. The basic part of it is if everything is symmetrical, meaning electrons are equally dispersed, so electrons are equally dispersed, that's probably going to be nonpolar. It's like things are up, down, side, and side. Everything's kind of equally dispersed. Then you're going to say, okay, everything's equal. Nobody has more electrons than another. Probably nonpolar because it probably doesn't have opposite sides or opposite ends. But sometimes you've got to kind of visualize that a bit more. So the one golden rule is that if your bonds are nonpolar covalent, meaning there's no like pushing or pulling of electrons one side or the other, generally your structure is going to be nonpolar. Okay? So generally if the bonds are nonpolar covalent, everything else is going to follow to be nonpolar. So that kind of makes things easier. But if things are polar can actually, two polar covalent bonds can cancel each other out. So for example, I'll draw one like this. If I have one atom here and one atom here, and the dipole is pointing this way, let's just call that A and B, and then I have the same thing but on the opposite side, the dipole is pointing that way, from A to B. If B and B are the same thing, same atom, same element type, and one's pointing that way and one's pointing that way, I think I drew that one bigger, but it's not bigger, not scale, okay? If one's going that way and one's going that way, they actually end up canceling each other out because they're saying this side is negative and this side is negative. I don't have opposite sides, I have same sides. Therefore, it is nonpolar. So the geometry does help things cancel dipoles out. So it's important to be able to draw it and think about it. If they don't cancel it out, then we're still polar because we have opposite ends. Famous example of a polar structure, water. Clipboard will work. Okay, water. So can I scroll down a little bit more? So if there's no writing, I'll scroll up if I need to again. So the geometry for water is what? What's the geometry? What's the shape? Bent. Bent. Okay, so you can see it's bent here. Which of these are H's?
The red one.
Say H2O. So how many H's? So H here, O. I will have people draw this on the test wrong. Do not be that person. Don't be that guy. Okay, so water is going to have a dipole moment pointing from hydrogen to oxygen because oxygen's more electronegative. Same thing this way. But what's here on water? 2 lone pairs. So tell me why the geometry is this way to even begin with. What are these lone pairs doing?
Pushing the hydrogen the other way.
Right, that's why this is even bent, because it's pushing those bound pairs away to make it have this bent shape. So anyway, this side over here is like very negative. This side over here is partially positive. So you can see opposite sides, opposite ends is what I usually say, polar. Okay, it's got poles. So that makes, this is the only reason we're learning about what the heck is molecular polarity is because we have to then derive the properties of polar compounds versus nonpolar compounds. So like polar molecules will have things like high melting point, high boiling point, high surface tension, cohesion, adhesion, things like water has. So that's what we're going to kind of get into tomorrow. Okay? So you guys want to do more example? Oops, let me go back here. This example, we went through that yesterday, or day before. Yes? We went through the whole thing. So the molecular polarity of it, I want you to tell me. Because you drew it already. You put chlorine, hydrogen, hydrogen, hydrogen. Okay, so you tell me what the shape is. Tetrahedral. So think of a tetrahedron. It's like one's up, one's to the side, one's to the side, one's to the side. Think chlorine up, okay? Where's the bond polarity pointing? On the carbon-chlorine bond and on the carbon-hydrogen bond. Which one was a polar covalent bond? Both of them? You guys wrote this down.
We didn't do this one.
Oh, which one did we do?
We did CS.
My bad. Okay, I'm doing this one for you right now. So tell me the bond polarity. You guys did this for homework, I'm saying. You did C to Cl. What's C to Cl? Is it polar covalent? Yes, because it's 2.5 to 3.1, 0.6 different, so you should have a dipole moment pointing from carbon to chlorine. So on the structure itself, you can do exactly the same thing. You're going to say, okay, that bond is pushing electrons north, just pointing it up. And then from carbon to hydrogen, 2.2 to 2.5, nonpolar covalent, so just put NPC, nonpolar covalent. Don't draw anything there. So tell me, is there equal distribution of electrons or unequal? Look at the molecule. You see no electrons, no electrons, no electrons, electrons!
Unequal.
Unequal, so that's going to be a negative region up here, so partially negative up here because those are all those electrons, and then down here, lack of electrons probably means partially positive. So that partially positive is kind of showing you opposite ends, so what do you say?
Polar.
Opposite ends means polar. I know you got to kind of drill that in your head, but opposite ends means polar. And that's all you write there, polar. That's it. Okay? So what I'd like for us to do today is to get through the first page, like the first half of this in building, and I am one person and you are many, but I have to check every structure and then ask you if it's polar or non-polar to clarify that you got it right. You are going to do this with a partner, so that means you got to check yourself, check yourself, you know, before you wreck yourself, but check and your partner because you guys need to work together. And I'm just going to be running around like crazy checking that. Okay, if you did not finish 85% of your structures, do not get up. You need to finish those first, and then you will go to the lab. Okay, I understand there were some that were more difficult. Oh, for example, anything that's got X xenon,
Yeah.
xenon can be above octet, so expand octet. And if you had, if the first element, if you have 3 elements involved, like XeOF4, I think is what it was, the first one is going to be your central atom. Xenon, for example, is your central atom. And if you have extra lone pair or extra electrons, throw them on the central atom because that central atom is the biggest and it can accommodate more than octet, generally. So I'll help you with that as you guys go. But like I said, partner up. I have the molecule kits in the back. You guys just have to make sure that you actually keep your molecule kit together. And let's go. If you don't have 85% of it done, do not get up because I've already seen it. I've already seen it, it's done or not.
For the lab, and that's really
Can you help me on this meeting thing?
Yeah, that one.
This was online if you is that why? There's no thing. I just remember she said that yesterday that they could have like a ton, so just hope for the best. Okay, so what's the thing? Then like how much is it? Something minus you. I got 2 points. I don't know how, but it's on there. What about bearing? Oh, I think I wrote down the right items. I got 0.09 and 3. Yeah, I did that. I was like, whoa. I don't remember. I remember. Because this was a metal. Yeah. You can't do like this is like so shitty kind of. I just look yeah, I was like right next to it, so I in grade. The dipole movement? Yeah. It's not hard, you just do little or big. So like, and like most of them. So that was probably. I just like figured out how many little legs have. Like I didn't have why? This is carbon, CO2. So maybe I don't know. I was probably thinking of H2 ligands and 0. Well, it's done in that's just I was right. Because if not, you can't do anything. So this is first.
Cut it down by.
I was so weird.
I gotta make some double bonds. Double bonds.
Alright guys, we need to get quick reminder in the lab before I make this one. Thank you. Reminder. Let's build like 3, call me over so I can check. And I'm gonna check off. I'm gonna check off on one person in the apartment set and then I'm gonna expect that they're all the same.
I forgot about that. How about that? No, they're together. Yeah.
One. That's not one.
Pretty much.
And then you have the two work on. So you put that on the table. Then you calculate how much.
How do you do the shape again on the back?
Everybody in the lab right now. Look at me. I have Miriam. I have very, I have oxide.
Because the CA
They're attracted. No bond. Because it's in the ionic bond, yeah? Ionic bonds are not bonds. Divide.
no, be one. I would like to explain more, obviously. So for the CLs, you actually said go through I'm sure it's complete.
Some of them have 2, and the ones that are 2 are the ones that are kind of whatever. So you do know how to do it. Kind of. Okay, so what if this is so you look at both of the elements and you look like FC for this one. But as you look at them, and remember you saw the little the one that has a one. So as this is what you saw the arrow going that way, and you subtract and go 4.0.
I will come back. I have another time for the lab. I have all you there.
Alright. So I go see it has 2. You realize how when you go to the for all of them, so like probably 2.5 and so I don't need that. I don't know how to do the
I counted down at the beginning, but now I'm so there would be 10. So 5
I'm seeing the same issues. So let me draw this one. I'm going to draw one of these. Let me tell you which one it is. All right, guys in the back and people in the front, look up here for me for xenon tetrafluoride. I just want to make sure we're on the right path. Xenon tetrafluoride. How many electrons total does it have? Electrons total. 36 electrons. Okay. So then you have xenon, and then you have fluorine, 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 fluorine. I think we all got to the point where we put octet on fluorines. How many electrons is that total? 32. Then you're like, oh no, what do I do with the other ones? You put the extra electrons on xenon as a lone pair and a lone pair. And I just put them on opposites. Now this shape is not on your sheet. I gave you minimal shapes. There are lots and lots and lots more shapes. You don't need to know all of them. So this one right here is really cool. What you need to find though is the little bead with 6 holes in it, because it needs 4 attachments and then 2 open sides to represent the lone pairs. What color is that bead? What color is it? Silver. It's a silver one. I see your hand. I'm coming soon. This shape is weird though. This shape looks like this. I'm going to try to use my 3D drawing skills again. It's a flat square. It's a flat square with a lone pair that's invisible and a lone pair that's invisible. But if you look at the flat square, it's a square and it's flat. Alex, what is this one called? It's a flat square. Square planar, right. It's a flat square, square planar, square plane, okay? I'm going to rotate, keep rotating around.
Oh my God.
Today.
Her elbow literally
No, I don't see anyone there.
Guys, I'm coming. I need to try You want to know that? Is that it?
The only issue that I'm hearing is culture and justice. I don't think that'll be a big vote. They'll absolutely stop it right now. They've already made our field. Take our time. Was she not? No. Okay, exactly. Yeah, I was going to say, like, no, she couldn't be mad. She's very aware. It seemed like they were. Yeah.
Alright guys, I'm giving you 5 more minutes. I'm going to try to make one less week. Do not build more because you know I'm slow. Okay? Yes. Start deconstructing if I've already started. Start deconstructing.
Well, the thing is, like, I was doing it right, and then all of a sudden it's wrong, and I went back to what I was doing wrong, and now I'm thinking it's right. I'm going, it's weird. So, because I was confused about the document, and then I honestly, yeah, I didn't realize that. Now I have to go back, and I'm still like, I'm putting completely on pause. They're like, I mean, I told them. But I mean, you might be a little that's one. I mean, I had every time I think it was got it.
Again, we
Alright guys, give me 5, 4, 3, 2, 1. I'm gonna wait with you. If you bother, I have you. If you not, please. I'm still waiting. Okay, deconstruct. Everything should get back in kind of organized fashion. It's not organized. Don't mind from your dreams. Like, look at the box people and put it in the right. There we go. Okay? It needs to look at it small. But I need to conclude some things together, of course, so we need to back up. Let's so I'm counting my head.
You elbowed me in the eye.
Okay.
Are we?
Our friend. Our friend. Come on. We're almost halfway
Okay guys, attention up here. Okay, we are concluding together. We are not done. I still have 7 minutes. Plenty of time to talk about bond angles. Okay, so on your notes, someplace where you wrote your shapes, I want you to indicate a couple of bond angles for me. So we will have about 40 minutes tomorrow to finish building. We'll have some time to talk about the structure some more. Thank you for being patient. Some of you guys were more patient than others, but you guys have to understand I have to come help a lot of people. So whenever we're talking about angles, it's easy now because you've seen the structures. Please do not pack up. Sit down. That is rude. Sit down, unpack, and come back to me for 5 minutes more. So whenever you built them, you were able to see a linear structure. The linear structure has a bond on the left, a bond on the right. What is the angle between left and right? If you think a whole circle is 360, then between left and right, what's that angle? 180. So I have it here for you, but I'm trying to indicate it to you through like images too. So that is something that you should easily know. 180 angle between linear legs. Okay. Whenever you get something that was like a trigonal planar structure, you had like, for example, boron trichloride without the electron dots, I'm sorry, but it was a flat structure and it had a leg, leg, leg. So it's basically 360 divided by 3. So what's that angle? 120. Do you see how that works? It's 360 around, but you divide it into 3, so it's 120, 120, 120. Okay? And then the tetrahedral is one that we kind of talked about at the beginning of class. If you look at a tetrahedral structure, you notice it's not exactly 90 degrees. It's got something more obtuse. So above 100 is good to know. Specifically, though, the angle is 109.5 degrees.
Are we going to need to know like the exact angles?
You will need to know generally. So like if I say linear, you should know 180. So like I think that these two are very easy. The tetrahedral one, you just need to know is above 90. If you visualize it, you know it's above 90. That's 109.5. The trigonal pyramidal, that was one where you had the PCl5, so you had a phosphorus in the middle, chlorine up, chlorine down, and chlorines in the middle. Well, chlorines in the middle are kind of like an equatorial region. Chlorines going up are like axial, think axis and equator. That angle is exactly what? 90. But in the middle, you had leg, leg, leg. So that's 360 divided by 3, 120. So that actually is 2 angles to it. But I think if you know the angles, it helps you visualize it better so that you can think about its polarity. So I'm just trying to pull some things together for you here. So that's 90 plus the difference between the equatorial region, which is 120.
And then I'm not going to do that one. We'll stick with that. Because that one's the one that was a square bipyramidal. But what I need you guys to do is tonight, you need to finish most of problem set 7A, which is a combined problem set. Because it's got loose thought structures, molecular geometry, polarity, and so forth. Because I want you to make sure you ask me questions so that I can answer those before review day. Okay? After that, I mean, we'll finish the dots tomorrow, but expect we'll kind of talk for about 30 minutes at the beginning of class, and then we'll finish up our dot structures. If you don't finish problem set 7A, and I don't expect you to tonight, because there's IMS, intermolecular forces on there, we've not talked about that, you'll have time to finish it tomorrow in class. Cross your fingers, yeah.
Will the IMS be
On the test, yes. Yeah, on Tuesday. Yeah, totally. Yeah.
This is all that was on my house.
It's more. It's a chart. It has a big chart. It has a chart that you have to fill out too. I can look online for you, but it's on there. Okay. The student pack has.
Like make your own chart.
Yeah, make your own chart, and it's got electron configurations as review on there. A couple of other things.
Oh, this?
Yes. Yes. Okay. So at the last last thing, you can pack up now, but I really need you guys to look at your polyatomic ions, okay? So if you need help with ionic versus covalent, I have some tips here. But you only crisscross things that are ionic. You shall not crisscross anything covalent. That is one big thing. And a lot of us start our acids, but we did not name them like an acid. So I think you were like, yeah, okay, I know my acids, and then you said not hydro. You didn't say hydro, or you didn't even say acid. So make sure that you review your notes on that. And I'll have your quizzes back to you tomorrow. I was in the lab the whole time, so I didn't get anybody stuff. Okay? Go ahead and pack up. Hold on to your lab, because we're finishing it tomorrow.
I'm not getting stuck in that traffic.
Like the
I think just
Good. I forgot I'm still videoing.